topic. Arithmetic sequences and recursion. We talked briefly about both of those last lesson and introed them a little bit. Your textbook is designed to sort of step that up quite slowly, so you'll build those skills as you go, but you might find that some of the work is a little bit patronising as well. So I'm hoping by the end of today's lesson you can define an arithmetic sequence recursively and sketch a linear model for the sequence. So there's a bit of a hint in there. Arithmetic sequences, if you're going up by a common difference each step, that creates a linear function. So you should recognise how the sequences look. This whole topic is really just another way for us to define linear functions, and the way we define it here does relate nicely to some context. So let's talk about arithmetic sequences and a couple of things here in colour and my examples. So my first example is the arithmetic sequence 3, 7, 11, 15 here. And this is an arithmetic sequence because it has a common difference between subsequent terms. So this first term is 3, the second term is 7. The common difference between those two terms is 4. So I've got a common difference of 4. This is called an increasing sequence. You can have decreasing sequences as well. And the first term is 3. And if you actually think about it, if you got the first term of a sequence was 3 and it had a common difference of 4, you know everything there is to know about that sequence. That's all you need to know. Once you know those two things, then you're set. And in actual fact, if you take this to the linear function stage, 3 is kind of like your y-intercept in a sense, and 4 is kind of like your gradient. So there's a direct relationship. It's basically just linear function, but rephased. The second one is a decreasing sequence. Common difference is what? 3 is close, but I want a little bit more information. -3, cool. So it is a common difference of 3, but we say it's -3. That removes the need for us to say it's a decreasing sequence. The -3 defines it as a decreasing sequence, and the first term is obviously 21. Any questions about that? So now we're going to talk about how we define it recursively. Recursive definitions are probably more logical. They're more obvious and easy to see and recognise for what they are, but they don't make things as easy when we actually get to the practical side of things. So you'll see that we're going to define it in nth term form as well, and that'll be less logical, more linear, a little bit more abstract, but simpler to actually determine certain values. So here's our recursive definition. The recursive definition defines the nth term as described by the previous term tn minus 1. I'm actually going to change this because I changed the previous stuff. We're going to say the n plus 1th term, or like that, as defined by tn. So it's probably important to recognise here, I would normally define tn by tn minus 1. So the nth term, or the 7th term, by considering the 6th term. So you tell me what the 6th term is, I can tell you what the 7th term is. But the textbook uses tn plus 1 defined by tn. So I'm going to stick with that notation, and it doesn't really matter which way you go. So tn plus 1 is actually the n plus 1th term, technically, and that's how the textbook does it. So what we get is tn plus 1, and this is written, think about it logically, tn plus 1 is equal to tn plus the common difference. So what we're saying there is that the next term is equal to the previous term plus the common difference. And if we go back to our original examples, you can see that happened. 15 is equal to 11 plus the common difference of 4. And that's a recursive definition, if we define what the next term would be based on the previous term. Are there any questions on that? That's it. We work with a first term. So a linear function can go on and on in any direction. Arithmetic sequences are usually loosely linked to some specific applications and context. And so we work with there's a clear and definite first term. We don't go before that. So typically you'll be working with T1 or maybe T0 in some cases, but nothing, you won't have term -1. So n is always greater than or equal to 1. So we had that definition there, and that's it. So an arithmetic, I don't know what happened there. I wrote these, and Mrs. Holmes is using them in her class, and she's going to be seeing these little things that I put in there. So example 1, the arithmetic sequence 5, 9, 13, 17 can be defined recursively as what? Any takers? I'll start with the left-hand side. Tn plus 1 is equal to what? Tn plus 4. So Tn plus 1 is equal to the previous term plus 4. I did hear Tn minus 1 there. You could define it recursively as Tn equals Tn minus 1 plus 4. Still saying the next term equals the previous term plus 4. So either of those will work. We know it's plus 4 because the common difference is plus 4 in each case. So we know that's the case. Any questions on it? Pretty simple, I think. So there's our notation. Just don't forget that notation there. They're the same thing. I actually consider y, but hopefully that's been covered. It also leads to this formula here, Tn minus 1 equals d, which you also already know to be true. This is just the algebraic way of writing something you know to be true, because if I go back up the top, when I said to you at the start of the lesson, what is the common difference in the first sequence, and you told me it was 4, you worked that out because you did 7 minus 3, or 11 minus 7, or 15 minus 11. So you knew it looked at the difference between two subsequent terms. And that is what this is saying. In pink, it's saying take Tn, some term, and subtract Tn minus 1, the previous term, and that will give you d, the common difference. So you know that to be logically true anyway. Now, just quickly sketching. Take the recursive sequence, Tn plus 1 equals Tn minus 2, where the first term is 3. So T1 equals 3. Term here, the first term is 3. What's the second term? 1, it is 1. Cool. What's the third term? Negative 1. What's the fourth term? Negative 3. So the recursive is the next term equals the previous term minus 2. So T1 is 3, therefore T2 is 3 minus 2, which is 1, and T3 is 1 minus 2, which is negative 1, etc., etc. Recursive definitions are great, but they're not great if I ask you now to find the 20th term, because then you've got to go through and go 3 minus 2, 1 minus 2, negative 1 minus 2, negative 3 minus 2, and you've got to do that 20 times. So they're not as helpful in those types of situations, but in sketching and stuff like that, setting up tables, so the graph will look like this. I've got n and I've got Tn. The first term is 3, the second term is 1, the third term is negative 1, the fourth term is negative 3, and you should get a linear function. It goes off in the right-hand direction, so right and down, but it doesn't go back in the left-hand because n starts at 1. But what you might see on occasions is that sometimes we start with term 0 and it starts on the y-axis. That's all right, but you'll never see it go into here. It'll never happen now. So that's how we sketch it. And you should get, with an arithmetic sequence, you should get a linear function. But you get negative values, which we got down here, but you won't have term negative 1. And technically, like mathematically you can, but in the applications and the definitions here, n is always greater than 1, equal to 1. And then occasionally, sometimes they use T0. Here's another example. An arithmetic sequence follows a recursive rule, Tn plus 1 equals Tn plus 3, and T1 equals 7. Set up a table and sketch the graph of this sequence. And that's the last thing we're going to do. So I'm going to give you 2 minutes to do that. And to be honest, I think that should take you no more than 2 minutes, with the exception of if you are one of those perfectionist too is going to have to draw their graph so neat that it could be in a textbook. Go. No, not looking at you, Sophie. It's all right. So I'm just going to run through this one quickly. I can't actually move. There we go. It's moving. So first I need to build the table, which shouldn't take too long. I've got N and Tn. I don't have to build it too big. If you're not given directions on how big to build it, probably 1, 2, 3, 4, 5 would be plenty. I'm told that T1 equals 7, and I'm told that Tn equals Tn, or Tn plus 1 equals Tn plus 3. That's telling me that each subsequent term is increasing by 3. So I get 10, 13, 16, 19. I've set up this axis, which is probably not ideal because I'm going to be working in the first quadrant only, but I'll work with it. The first thing I'm going to do is plan my axis. So I know I need to go up to, this is my Tn column here, and this is my N column. Going up to 5 is fine. That's 5 there. And so 2, 3, 4. I want to use up as much space as I can. And I need to go up to 19. So 5, 10, 15, 20 is not bad. I might actually go up in 4s. So you just want to go up in a reasonable number. 4s are all right. You don't want to go up in 3s. You don't want to go up in 7s. Any weird prime number, try and avoid anything that's factors of 2 and 5. So 2, 5, 10, 20, 40, those are good numbers to go up in. So I'm going to go up in 4s in this case. The first term is 7, just here. The second term is 10, which is there. Third term is 13, and then 16, and then 19. And my sequence graphically looks like that. And that's all I had to do. That shouldn't take you any more than 2 minutes, as long as you know what you're doing. Are there any questions? So this is my little success criteria at the end of each lesson, which I'll leave up. And you're now working on and can do all of exercise 4B. Can you define an arithmetic sequence recursively? If we give you the key features, can you then make the recursive function? Can you determine the common difference and subsequent terms? And can you develop a table and graph of an arithmetic sequence?